Everybody has a good story about Mark. I don't. So, bonne fête. I don't recall at all when I met him first, but it must have been in one of those symposium workshop here at the Phil Institute or at Edmonton when I visited the university there. But I owe him a paper. I still remember that. But I'm writing too many books. I don't have time to write that paper. This talk is a collaboration with my postdoc, Tiziana Gelmi Cadanso, hard to pronounce, I will just say Tiziana, where we are trying to understand the movement of small carnivore, mesocarnivore like coyotes and foxes in an urban setting like Toronto. So movement is crucial, and we have seen movement could mean migration, dispersal, or moving through your home range. And in ecology, there's a lot of concern about it because we are fragmenting our landscape. And there's more and more a notion of maintaining connectivity for conservation that is pushing Park Canada to have an initiative now to promote connectivity throughout Canada. So connectivity is very important, and it's really linked to things, how the animal is using a region and how the animal is able to move. But specifically in urban setting, there's a lot of different conditions, and each other neighborhood is different from one another. So that's the difficulty, right? So this very nice review is stressing a lot of aspects that could be important to consider while looking at the movement of animals. And I would say that the elephant in the room is the lack of data. So especially in the cities. So basically, I'm personally interested in how the animal will move in different configuration. And the things that are lacking is to have actual real data that is specific to the context in which they have to move. So we are left with excellent data from telemetry, maybe tags or those colors. So those are the best data that we can have. Camera trap are more and more used, and citizen science. So all those type of data have different characteristic and plus and minus. So basically with telemetry data, we know very well locally. I mean, it could be the home range and more, of course, depending on the number of animals, how they use a landscape. Then to camera trap, the problem is that you're seeing only what is in front of you, and it's you have a presence. You can assess the absence of data with the number of images that you have. Then there's citizen science where I'm not sure who we are studying. Are we studying the animal or the human behavior? So it's maybe a confounding effect. And then when everything goes wrong, we just simulate data, right? So we do individual-based model where we expect that there will be some emerging property that can be raised. So I was hoping to present some work on the camera trap, but it's not ripe for the moment. So I will focus on the telemetry data and some citizen science data that are asking how the animals are moving or where they are in the city. So this work is in collaboration. Like I said, my postdoc Tiziana is the main author, and a series of co-authors that are working on, we changed so much name, the Ontario Ministry of Natural Resource and Forestry, myself and some colleague at the Toronto Conservation Authority. So the information that we have is telemetry data that the ministry let us use. And what we want to assess is how the connectivity change depending if we have resident coyotes versus or transient one, and is the behavior change during the day or the night? That's the kind of idea that we have, that the animals are maybe using the city much more during the night where there's less human activity. So the context is really that we will use some kind of vegetation data that is decreasing. There's a lot of human population that is increasing, a lot of building roads that are intervening the movement so that the animal need to adapt their range, the size of their range that they are using, their diet, maybe they're shifting their vision activity, and maybe they're more nocturnal. So here is the Greater Toronto, where we are. I don't know where we are. I have no clue where we are, but we are close. We are close here about. And all the dark dots that you cannot see because there's many of them are telemetry data for 27 animals. That was about 2 years of data over a period of 10 years or so. And some animals have different behaviors. So the home range could vary from 3 square kilometers to 26 square kilometers. Some are residents, some are transient. So just to give you an idea, there's a very small home range location of data points for one individual there. There's maybe more occupancy of space for another individual. Then there's more land use. Movement for this yellow individual, and then this one we need to move outside the city. That's definitely a transient animal. So those are the different kind of behavior, but because we have the telemetry data, it allows us to do methods that are more known to this group, is to assess how much the landscape is favoring or not the movement of animal in the city. So we're going to use vegetation data by means of NDVI. We're going to look at the building impervious landscape information, the population, human population density, and the different level of roads that there is in the landscape. So then we are going to use the step selection function, combining all those layers and the telemetry point to assess how the animals are perceiving the landscape. So this is the Great Toronto region here. And we are going to use this habitat stability map for 2 purposes. Here I want to make a parenthesis. I'm not Danielle Fortin, I'm Marie-Josee Fortin, and we are not related. So this method of step selection function was developed by the other Fortin, not me, but I'm using it. So here we've been using it to assess this kind of relative selection strength for the different layers and different moment in time and transient and resident species. So we put all of this together to get this map. And we need, in conservation and connectivity, we need to have patches, right? And since we want to assess not only the location where we had telemetry point, but for the entire region, we have to select which level of habitat suitability would be a patch. So we had this kind of harsh threshold of 1%. We tried several of them, but for the purpose here, we use 1%. So the highest amount of suitability is considered as patches. And now we want to assess how they can move in the landscape, giving all those layers that I showed you, and if they are resident or transient. So now I know I uploaded and there's a mistake, but basically to assess the resistance value, we didn't use expert knowledge. We used the information that the animal gave us, and we used the reverse of the relative selection strength, and then we map that like we see here, and then we assess the connectivity throughout the landscape. So this is the resulting connectivity map. More yellow it is, more connectivity it is, more purple, less connectivity. And the different regions that we are showing here are different landscape aspect of the GTA. So we have some area here, and the number I here is there's a power line, and underneath there's vegetation. Then there is a case number 2 here. Whoops, there's a ravine and a golf course, so it's more yellow, so there's more movement. There's a commercial region, so there's no connectivity at all, they don't go there. And then there's more residential, well, I cannot say it, neighborhoods where people live, sorry. So there's very different aspect throughout the landscape, but really what we wanted to assess is which of those characteristics is the age of the animal, the sex, the status of being transient or resident that is important versus is it night and day, the winter, summer months, and then the reproduction phase. So the things that was, the models that were significant was only those that include day and night and the status of resident or transient. So we had now mapped the result according to those behaviors. So now you see that, well, I don't want to go back, but the maps are different. And basically what we are seeing, there's more use of the landscape at night than during the day for some location. And the transient animals are moving in different fashion than the other ones. So here, in conclusion, the movement is changing according to the fact that the animals are either resident or transient. If they are resident, they will have maybe longer path in forested region during the day, and the transient one during the night, they just go more faster to some location. But the key things here is that those neighborhoods and road in residential area are key for this dynamic. So the roads are used at night by the animal. So good. I have wanted to present another project on animal movement, but this one is host-parasite interaction. And there is a lot of change in the environment, and we are interested to see, can we see if there's more parasite or more homogeneous individual in downtown than in the suburb. So there's this organist, Toronto Wildlife Center, that have vets that will identify the host parasite within animals host, and the animals are brought by human. So let's say that I'm at the corner here of St. George and College, and I see a poor animal that doesn't seem to be very healthy, and I'm a good heart. I will bring it to the Toronto Wildlife Center, and then they will try to revive, cure the animal, and they will do a screening of the parasite that they have. So Alex Watt took a very patient time to go through all those, because not through all the years, all the same criteria were used to assess the parasite of the individuals. So there were about 3,000 data that we could use. And of course, now we have the XY coordinate and the time, but then there's too many locations. So we regroup the information in cells of 1 by 1 kilometer, and then we assess just bipartite network and result. So just to show you no good surprise that there's a lot of population downtown Toronto, and all those dots are even information of animal that were far away were brought at that center, and it covered a wide range of rural and peri-urban and suburban. So the host diversity, surprise, surprise, a lot of squirrels, as we expect, a lot of pigeon, a small raccoon, some bats, some sunbirds, so in minority. And then for the parasite is mostly viral bacteria, nematode, fungi, and ectoparasites. So a wide range, and then we split the information into categories of range of urbanization from more rural to more downtown Toronto. And I know it's difficult to see, but there are differences. And the big bar are, let's use this pointer properly. There's a pigeon, a small carnivore, and then there's viral. And as you move, there are changes. And I know it's hard to trust me, but here maybe you will see it better. So we organize the information in terms of the species strain. So here what we can see that in the rural for the host is mostly sunbirds that are dominating. Then in the ex-urban is more the small carnivore. Then the pigeons start to be the most important host. Then for the parasite is the same thing. We have a change from more ectoparasite to more even distribution of viral and ectoparasite. And in the middle, the interface between very urban and more rural, it seems that we have those compromise of interaction. And we think that this is where there's maybe more habitat, more resources, where the species are maybe interacting and exchanging those parasites. So to conclude, there's more generalist hosts and parasite in downtown urban setting, and that the interaction are maybe at the suburban region where there's more diverse habitat and more food for the species. So to conclude, basically here, I think that to get to the other idea of perception and learning, we need to make sure that we're not having the bias of the human, like I showed you with the citizen science, and that more telemetry points will be needed. So I would like to thank you, Tiziana, obviously, Alex Watt, Andrew Chin, and the collaborator in the ministry. Thank you.